Hey guys, my name is IBM and today I'm solving February-March 2024 paper 4. The question paper is attached in the video description. You can check in my Google Drive. You will be able to download the question paper. By the end of this week, all AS and A-level papers, including IGCSE papers, will be solved in my YouTube channel. So without wasting time, I would like to take you to the question paper. So this is Cambridge International AS and A level. This is going to be Feb March. So it is Feb March 2024. This is paper 4.2. This is the most important paper for those of you doing only A levels. Even if you are doing AS and A level, you should make sure that this paper is part of you. You should spend much time revising paper 4. So let's start. Question number 1. Explain why the gravitational potential near to a point mass is negative. So if you consider a point mass, remember for a point mass, the gravitational field lines are radial and they always point towards the center of the point mass, which means the force is always attractive. And also remember that gravitational potential is defined to be 0 at infinity. So to answer this question, I will simply say number 1, gravitational potential at infinity is 0, and the gravitational force is always attractive. So if the gravitational potential at infinity is 0 and yet the force is always attracting everything, it means if I move a mass to infinity, it means work is done on that mass. If I move a mass from infinity towards another mass, it means work is removed from the mass. So gravitational potential at infinity is defined to be 0, and the gravitational force is always attractive. So work is done on a mass to move it to infinity. So work is done on. So work is done on a mass to move it to infinity. So you are doing work between zero at infinity and another value. So it means between 0 and another value, the other values are going to be, because infinity is the biggest, yet at infinity potential is 0. It means between infinity and any other point, the work done is going to be negative. So work is done on the mass to move it to infinity. So we are moving through negative values. A planet may be assumed to be a uniform sphere. It has a gravitational potential phi at a distance r from the center of the planet. So the variation with 1 over r of phi is shown here. So we know that gravitational potential phi is defined as negative g, capital M, over r. And they have given us a graph of phi against 1 over r, which means the gradient of this graph is going to be negative g times m. The gradient is going to be negative g times m. If we plot phi is equal to negative gm times 1 over r, they have plotted phi against 1 over r. Show that the mass of the planet is 8.8 times 10 to the power of 25. So I will say from phi equals to negative g m over r, this is negative. It means that the gradient is equal to negative g times m. So I want to find m. So m is going to be negative of the gradient divided by capital G. So this is going to be negative of the gradient. So I'm going to choose 2 points from the graph. Then I'll divide this by G, which is 6.67 times 10 to the power of minus 11. So I'm going to choose points from the graph for the gradient. So this is, I'll choose this for 0. Now I'm looking for another favorable point, favorite point. Let me take this point here. So that is negative 2.0. That is for potential. Then on the x-axis, on the x-axis I have this is 3 point. The scale is 0.05, 3.1, 3.2, 3.3, 3.4. That is 3.4. So this is going to be equal to the negative of 2.0, of course, minus 0. This is times 10 to the power of, I'm finding the gradient. This is times 10 to the power of 8 divided by the change on the x-axis, which is 3.4, 3.4. Then times 10 to the power of minus 8. So this is over 3.4 times 10 to the power of minus 8. So this is, of course, minus 0. That is on the x-axis. Gradient over g. So I'll just press my calculator. So I hope I didn't take negative. Okay, it's negative 2. So I will just divide this. I have the negative, of course, is going to cancel out. So I have 2 divided by 3.4 exponent. Okay, it is 2 exponent 8 divided by 3.4 exponent minus 8. So this is, of course, the negative has cancelled out. Then I will divide this by 6.67 exponent minus 11. So this is giving me 8.819 times 10 to the power of 25, which is approximately 8.8 times 10 to the power of 25. Okay. Then the period of rotation of the planet is 0.72. So this is capital T. A satellite in orbit around the planet remains above the same point. It remains above the same point on the surface of the planet. Use the mass of the planet to determine the radius r of the orbit of the satellite. So if it is remaining at the same point, simply because the gravitational force is equal to the centripetal force. So I will just equate capital G, capital M, small m over r squared to m v squared over r. So this is going to be capital R. But remember, v is equal to omega times r. So we want to find the radius. They gave us the period. So v is going to be, omega is 2 pi over t, then times r. The small m has cancelled, one r has cancelled. So I have capital G m over capital R is equal to v squared, which will be 4 pi squared r squared over t squared. So I must make r the subject. So I have that g m t squared divided by 4 pi squared is equal to r cubed. So r is going to be equal to the cube root of g, which g is 6.67 times 10 to the power of minus 11 times m, which is 8.8 times 10 to the power of 25 times the period, which is 0.7. The period is 0.72 Earth days. So the period is going to be 0.72 times Earth days. So that is going to be times 24 times 3,600 to change it to seconds. This is going to be squared, divide by 4 pi squared. Okay, this is going to be to the power of 1 over 3 because it is the cube root. So I'll check this, 6.67 exponent minus 11 times 8.8 exponent 25 times 0.72 times 24 hours times 3,600, but this should be squared. Then I'll divide this by 4 pi squared. What have I left out? I'll have to repeat this. G is 6.67 exponent minus 11 times 8.85 exponent 25 times 0.72 times 24 times 3,600. But remember, this is squared. Divide by 4 pi squared. Then I find the cube root of the answer. So this is giving me 8.3 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. So this is 8.3 times 10 to the power of 7. The speed of the satellite in B is 8,400 meters per second. The mass of the satellite is 1,200 kilograms. Determine the additional energy required to move the satellite from its orbit to infinity. Of course, we know that at infinity, kinetic energy becomes 0. At infinity, let me use initials. At infinity, kinetic energy becomes 0. KE at infinity is equal to 0. KE, potential energy at infinity is also equal to 0. So, but of course, potential energy on the surface, E potential on the surface is equal to negative Gm of small m divided by R, and kinetic energy on the surface is half mv squared. But at infinity, each of them is 0. So that means change in potential energy is going to be equal to 0 minus negative Gm small m over R, and change in kinetic energy is going to be equal to 0 minus half mv squared. So that means total change in energy, total change in energy, total change in energy, which I'll call delta E, is going to be the sum of these two. So it will be 0 minus negative that gives us G capital M small m over R plus 0 minus that, which gives us negative half mv squared. So I'll just substitute in this expression here. This is going to be total change in energy, which is going to be required to reach infinity. So this is going to be equal to G, which is 6.67 times 10 to the power of minus 11, then M, which was 8.8 times 10 to the power of 25, small m, which was 1,200, divided by R, which was, I think it is 8.3 times 10 to the power of 7. This is change in potential energy, minus a half times 1,200 times V, which is given as 8,400, but this is squared. So I'll just press my calculator. 6.67 exponent minus 11 times 8.8 exponent 25 times 1200 divide by 8.3 exponent 7. Then I'll just say minus, open brackets, a half is 0.5 times 1200 times 8400, but this is squared. So I'm getting 4.25 times 10 to the power of 10 joules. Question number 2. By referring to both potential energy and kinetic energy and potential energy, explain what is meant by internal energy of an ideal gas. So since it is an ideal gas, for potential energy, we shall say this one is equal to 0. So remember, internal energy is the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. But for an ideal gas, potential energy is 0. So I'll simply say the sum of the random distribution of the potential energy and kinetic energy of all molecules that make up the gas, but for an ideal gas, potential energy is 0. We know why potential energy is 0. The reason is because intermolecular forces are negligible, since because the intermolecular forces are negligible, then potential energy component is 0. The potential energy part depends on the intermolecular forces, and if there are no intermolecular forces, then the potential energy component is 0. So for an ideal gas, internal energy is just the sum of the random distribution of the kinetic energy of all the molecules which make up the system. Okay. The fixed mass of an ideal gas at a temperature of 20 degrees Celsius is sealed in a cylinder by a piston, as shown in the figure. The initial volume of the gas is 1.24 times 10 to the power of minus 10 meters cubed, minus 10 power minus 4 meters cubed. Thermal energy is supplied to the gas and its volume increases by 5.2 times 10 to the power of minus 5 meters cubed. The piston is freely moving so that the gas is always at a constant pressure. So pressure is constant. Atmospheric pressure is 1.01 times 10 to the power of 5 pascals. Capture the work done by the gas. So since the gas is pushing, the volume is increasing, so the work done by the gas is going to be positive, and the work done on the gas would be negative. If we wanted the work done on the gas, it would be negative because the volume is increasing. But since we want the work done by the gas, then it is going to be positive. So the work done is going to be pressure times change in volume. So the pressure is 1.01 times 10 power 5. Then the volume increases by that, so I'll say times 5.20 times 10 to the power of minus 5. So this is 1.01 times, or exponent 5, times 5.2 exponent minus 5. So this is giving me a positive 5.25 joules. I'm saying the work done by the gas is positive because the gas is expanding, but the work done on the gas would be negative because instead the volume is increasing. Then calculate the final thermodynamic temperature of the gas. So using a simple formula, PV over T equals to a constant. The pressure is constant, so I would simply say V, or if you want, you can say P1 V1 over T1 is the same as P2 V2 over T2, but remember pressure is constant, so P1 and P2 are the same, so I will just remain with V1 over T1 is equal to V2 over T2. So I will just make substitution. V1, our initial volume is 1.2, V2 is 5.2. No, V2, because the volume increases by this, so the final volume is going to be 1.24 plus 5.20. That is V2. V2 is going to be the sum of those two because this is the increase in volume. So this is going to be 1.24 divided by T1. T was 20 degrees Celsius, so 20 plus 273. So this is over 20 plus 273. To change it to Kelvin, should be equal to V2, which is 1.24 plus the increase in volume, which was, by the power of 10, here is minus 5, here is minus 4. So here I will add 0.520. So this is plus 0.520 divided by the temperature T2, which is called just T. So what is T? I'll make T the subject. T is going to be equal to 1.74, just summing up that, divided by 1.24 times 293. Note that I ignore the power of 10 because it cancelled out, times 10 to the power of minus 4 times 10 to the power of minus 4, and this one cancelled out. So I have 1.74 divided by 1.24 times 293. So this is it 293? Let me first add again. 1.24 plus 0.52. This is 1.76. So 1.76 divided by 1.24 times 293. So this is 415, or approximately 416 Kelvin. Then calculate the specific capacity C of the gas at this pressure. So we know that Q is equal to MC, change in temperature. And of course, it means specific capacity is going to be energy, which is 960 joules, divided by the mass is 16 grams, which is 16 times 10 to the power of minus 3. Then I'm making C the subject. Remember, C is equal to Q over M times delta T. Temperature change was, we have this is 416, the other one was 20 degrees Celsius, which is 293. So the temperature change is going to be 416 minus 293. So this is going to be 960 divided by 16. Let me first subtract this. 416 minus 293 times 16 exponent minus 3. Then I will say 960 divided by the answer. So this is 487.8. 487.8, or approximately you can write 490. That is to two significant figures. Never write answers less than two significant figures. The gas in B is allowed to return to its starting temperature. The piston is now fixed, which means change in volume is going to be 0. Remember, work done is equal to pressure times change in volume. If the piston is fixed, so I'll start with that statement. If If the piston is fixed, that means there is no change in volume. So no work done. So there's no work done by the gas. Okay, so here work done is equal to 0. Thermal energy is supplied to increase the temperature to the same final temperature. So it is again from 20 degrees Celsius to 416. That means it is the same temperature change. I want you to remember that change in temperature is directly proportional to change in internal energy. So I will still say since temperature change is the same, temperature change is the same, the change in internal energy is also the same. Change in internal energy is the same. Okay, so use the first law of thermodynamics to suggest and explain how the specific capacity of the gas for the situation compares with the value in B. So from the first law of thermodynamics, of course, Q is going to be equal to, or if we know change in internal energy is equal to Q plus work done. Here we now know that there is no work done, which means Q is only depending on the change in internal energy, and the change in internal energy is the same. Since Q is only depending on the change in internal energy, it means Q is going to be less. In the previous case, Q was more because there was work done. More thermal energy was to be supplied. Here, Q is going to be less because there is no work done. So Q is just changing the internal energy. So we can simply say less thermal energy needs to be supplied. There is less thermal energy is going to be needed here because the energy is only going to change internal energy, and yet the change in internal energy was the same as the previous case. So less thermal energy needs to be supplied, and from Q is equal to MC delta T. Since less Q is supplied, it means also the specific capacity is going to be less. So the specific heat capacity is less. In the previous case, the energy supplied was to change the internal energy and also do some work. Yet here, the energy supplied is not doing any work. It is just causing a change in internal energy. And remember, the change in internal energy was the same as before. So it means a small amount of energy is going to be required in this case. Therefore, a smaller specific heat capacity. Okay. Question number 3, that is simple harmonic motion. A small object of mass 24 kilograms rests on a platform. The platform is attached to an oscillator as shown in the figure. The oscillator moves the platform up and down. The total energy of the oscillations of the object is 2.2 times 10 to the power of minus 4. In one oscillation, the object travels a total distance of 14 millimeters. So let's check. This is equilibrium position. One oscillation means if the object starts from equilibrium, it moves to the highest point, that is a quarter cycle, coming back half a cycle, going to the bottom 3/4, coming back, that is now one cycle. Remember, amplitude is this vertical distance here. This is x naught. So this is x naught, x naught, x naught, x naught. So it means 14 millimeters is equal to 4 times x naught. So it means the amplitude x naught is going to be 14 divided by 4, which is, I think, 3.5 millimeters. Okay. So we know that energy is equal to a half m omega squared times x naught squared. So the energy is given as 2.2 times 10 to the power of minus 4, which is going to be equal to a half times the mass, which was given as 24 grams. So that is 24 times 10 to the power of minus 3. That's the mass, times omega squared, which is not known. The amplitude is 3.5 times 10 to the power of minus 3. But this should also be squared. I'm just going to press my calculator. So 2.2 exponent minus 4. I'll multiply this by 2. Then I'll start dividing. I'll begin by dividing this with 24 exponent minus 3. That is the mass. I will again divide by 3.5 exponent minus 3, but this was squared. Then I'll find the square root. So this is giving me 38.7. So omega equals 38.7. If you want, you can write 39. Then the frequency of the oscillator is fixed. So F is fixed, which means omega is fixed, because remember omega is equal to pi F. So if F is fixed, omega is fixed. And the amplitude of the oscillation is gradually increased. Calculate the maximum amplitude of the oscillation so that the object does not lose contact. If it tends to lose contact, then at that point the acceleration is equal to g. In case of losing contact, in case of just losing contact, the acceleration is going to be g. In case it just loses contact, it means it's just under the influence of its mass. So its acceleration is just equivalent to the acceleration due to gravity. And remember, acceleration is equal to negative omega squared times x. So I will simply say the acceleration, which is 9.81, is going to be equal to omega squared, which is 38.7, then times x naught. Remember, this is squared, times the amplitude, which is, I've just called x naught. So it means x naught is going to be equal to 9.81 divided by 38.7 squared. 9.81 divided by 38.7 squared. So this is giving me 6.55 times 10 to the power of minus 3. If you had rounded off this to 39, you will get an answer which is very close to maybe 6.4 times 10 to the power of minus 3 meters. But of course, the examiner will choose the tolerance. When I use this, I get a more exact value than the other one. So both answers will be credited. The amplitude of the oscillation is increased so it is greater than the value in B. Okay. State and explain the position in an oscillation where the object first loses contact. So the amplitude is increased so that is greater than the answer in B, Roman 1. State and explain the position in an oscillation where the object first loses, of course, the object first loses contact when it is actually at the highest point, when the platform is at the highest point, or when it is at the maximum displacement, but that is basically at the top of its oscillation. If you have watched my videos of simple harmonic motion, you must have seen such a question. I have already answered it. So this is at maximum displacement in upward direction. In other words, I'm saying at the top of oscillation, of its oscillation, at the top of its oscillation. But why? Of course, we know at the top of its oscillation, the contact force. Remember, if this is the platform and this is the object, its weight is acting downwards and the contact force is acting upwards. At the highest point, the contact force decreases, and at the highest point it becomes zero. That means the resultant force is only going to be the weight downwards. So I say that maximum displacement in the upward direction, since it's where, or it's the point, it's where the contact force becomes zero, or in other words, it is minimum. It's where the contact force becomes zero, it's minimum, and if the contact force is zero, that means the resultant force is maximum, and resultant force is maximum downwards, which means the greatest downward acceleration is at this point, which means the greatest downwards acceleration occurs at this point, or at this position. And remember that that point will be 9.81. So since it's where the contact force becomes zero, minimum, and the resultant force is maximum, and which means the greatest downwards acceleration occurs at this point. So that's where the object first loses contact. Okay, that is question number 3. Question number 4, 3 capacitors are connected as shown. So we see 2 are in parallel, and remember in parallel we just sum them up, 10 plus 20, which gives us 30. So 30 microfarads is in series with this. For capacitors in series, we consider them the way we consider resistors in parallel. So capacitance in parallel is going to be 10 plus 20, which is equal to 30 microfarads. Then total capacitance is going to be the product, 30 times 45 divided by the sum, which is 30 plus 45. 30 times 45 divided by 30 plus 45. So this is 18 microfarads. A capacitor of capacitance 45 microfarads is connected to a variable power supply initially set at 8 volts. So this is let this be V1. The output power supply increases so that the potential difference across the capacitor is 9.6. So this is V2. Actually, the increase in energy stored in the capacitor. So we know that energy of a capacitor is a half CV squared. So we want the increase in energy. So it is going to be a half C, let's say V2 squared minus V1 squared, or a half CV2 squared minus a half CV1 squared. So this is going to be a half times the capacitance, which is 45 times 10 to the power minus 6 into, this is going to be 9.6 squared minus 8.0 squared. Now the mistake is people first subtract before they square, which is wrong mathematics. 9.6 squared minus 8 squared. Then I'll multiply this by 45 exponent minus 6 divided by 2. So this is 6.34. 6.34 times 10 to the power of minus 4 joules. A sinusoidal AC power supply is connected to the input of a bridge rectifier. The output of the rectifier is connected to a load. Complete the circuit by adding a capacitor to smooth the PD across the load resistor. So here we have the output. These terminals are showing the output from the bridge rectifier, so I don't need this space here. I'll just join this space. But then we need a capacitor for smoothing, and the capacitor is connected in parallel with the load. So that will be the connection. The variation with the T of the PDV of the smooth output is shown in the figure. So we start with 4, this is V naught. Then it is smoothed up to this point. The scale is 1/5, which is 0.2. So this is going to be 3.2 volts. This is going to be V after discharge. Then the time of discharge, if we start from 5, discharge is stopping here. So this is the time of discharge. So from 5 to 10, here the scale on the x-axis is 5/10, which is 0.5. So 11, 12, 13. So this is 13. This is 5. So that is the difference is 8. 13 minus 5, which I think is 8. So determine the time constant in milliseconds of the smoothing. The time we have got there is time for discharge, not the time constant tau. The time constant tau is R times C. Or we can use the discharge equation where since we have V, we shall say V equals to V naught e power minus T divided by tau, where remember tau is R times C, which is the time constant. Small t is the time of discharge. So V is 3.2, V naught was 4.0, e power negative, time of discharge is 8 over the time constant tau. Introducing ln, ln of 3.2 divided by 4.0 is equal to, when I introduce ln this side, I will get negative 8 over tau. So if I make tau the subject, tau is going to be negative 8 divided by ln of 3.2 divided by 4.0. So from the calculator, I'll start from the denominator, ln of 3.2 divided by 4.0. Then I have negative 8 divided by the answer. So I'm getting 35.85 or approximately 36. Or I can write 35.9. 35.9 milliseconds. It is milliseconds because I didn't change the time. I didn't change the time from milliseconds, so it is, the time was in milliseconds, so I didn't change the time. A sinusoidal AC power supply has a maximum power of 16 watts. This is maximum power. State the value of the mean power when the output of the power supply is full wave. Remember, for full wave, all cycles, the half cycle, the second half cycle is converted. So if this is maximum power, minimum power is going to be half of this. So the average, the mean power here is going to be half of maximum, which is going to be 16 divided by 2, which is going to be 8, say 8.0 watts. Then for half wave, remember the half cycles are missing. So for half wave, this is what we have. You have one half cycle, the second half cycle is missing, another half cycle, the second half cycle is missing, which means the mean power for half wave rectification is again half of that. For full wave is half of full wave. So because a half of a cycle is missing, we shall again divide the full wave, the average power for the full wave by 2. So this is going to be half of 8.0, which is going to be 4.0. So this is 4.0. And we know the disadvantage of half wave is that it reduces the average power available because half of the cycles are always missing. Okay. Then an object travels in a circle at constant speed. State the names of two quantities that vary during the motion of the object. So if an object moves in a circle, the following varies. Because direction changes, the velocity changes. So number 1, velocity. And remember, momentum is mass times velocity. If velocity changes, the momentum changes. Number 2, momentum. Remember, also force is equal to the rate of change of momentum. If momentum is changing, it means the resultant force is also changing. Number 3, resultant force. And remember, resultant force is equal to mass times centripetal acceleration. So number 4 is going to be centripetal acceleration. And of course, if the centripetal acceleration changes, remember centripetal acceleration SC is equal to V over V squared over R, and V is equal to omega R. So it means omega is also changing. So not omega, omega is going to be constant. Omega is going to be a constant. But how about the angular displacement? Because the angular velocity depends on angular displacement. So there should be a change in angular, because omega is equal to delta theta over t. If delta theta does not change, then omega is not, we don't have angular displacement. We don't have angular velocity. So here we shall have angular displacement. This varies. So you can't fail to state only two. For any body which moves in a circle, the velocity, momentum, resultant force, centripetal acceleration, angular displacement, all these ones vary. A charged particle of mass m with a charge q enters a region of uniform magnetic flux field perpendicular to the field lines. The magnetic flux density is B. The particle travels in a circle. So we can say the magnetic force provides centripetal force. Magnetic force equals to the centripetal force. So I will just simply say BQV equals to mv squared over r. And you also know that, of course, one v cancels. And we also know that v is equal to omega r, which is the same as 2 pi over t, because omega is 2 pi over t, then times r. So I'm having that BQ is going to be equal to m over r times, where there is v, I'm going to put 2 pi r over t. So this r cancels with that one. So I remain with the BQ equals to 2 pi m divided by t, which means that B is equal to 2 pi m over q times t. The particle is an alpha particle. We know an alpha particle has mass 4u. It has charge twice e. The period of the circular motion is 2.5 microseconds. So that is times 10 to the power of minus 6 to change it to seconds. Calculate B. So I'll just substitute in this expression. So B, which is equal to 2 pi times m divided by q times t, is going to be 2 pi times m, where m is 4u, which is 4, times u is given as a constant 1.66, times 10 to the power of minus 27, that is the unified atomic mass unit, divided by charge, which is 2 times 1.6 times 10 to the power of minus 19, times period, which is 2.5 microseconds. So this is 2.5 times 10 to the power of minus 6. Okay, I've just pressed my calculator. 2 pi times 4 times 1.66 exponent minus 27 divided by 2 times 1.6 exponent minus 19. I'll still divide by 2.5 exponent minus 6. So this is 0.052. 0.052 Teslas. A second alpha particle is in the same uniform field. It travels in a circle of radius twice r. State and explain how the periods of the motion of the two particles compare. When I look at the expression B equals to 2 pi m over qt, it is in the same field, which means B is constant. it is still an alpha part which is m is constant. It is still an alpha part which is q is constant. So since b, q, and m, since b, q, and m are unchanged, and t, we don't see r in this expression here, and t is independent of the radius. So the period is the same. So the period is the same. Okay, so the period is going to, the speed of the alpha particle in B is 1.1 times 10 to the power of 6 meters per second. An electric field is applied so that this particle now moves with a constant velocity. So it means the electric force is going to be, or an electric field is applied so that this particle now moves with a constant velocity. So if the particle is now moving with a constant velocity, it means the electric force is actually equal to the magnetic force. Otherwise, if they were not equal, then it wouldn't move with a constant velocity. Use your answer in B Roman 2 to calculate the electric field strength, E. Give the unit with your answer. So the electric force is equal to the magnetic force. So I'll say electric force is charge times electric field strength. The magnetic force is B, Q, V. So of course Q cancels out, which means E is going to be B times V, which when I substitute, I think B will go to 0.052. Is it? Yes, 0.052 times V, which is 1.1 times 10 to the power of 6. So 0.052 times 1.1 exponent 6. So this is 57200. And the unit, of course, since this is E, electric field strength is newtons per coulomb, or it is volts per meter. So I'll just write here newtons per coulomb, or you can write volts per meter. Question 6. A small coil C has 64 turns. So this is capital N. And cross-sectional area 0.71 centimeters squared. This is capital A. The coil is placed inside the solenoid as shown. The center of the coil C is on the central axis of the solenoid. We know that, remember, B in the middle of the solenoid is uniform. And it is uniform and constant inside a solenoid. Even if there's a current, because the current is constant, B inside the solenoid is constant. There is a constant current in the solenoid. Coil C is moved through the solenoid from position X to position Y. On the figure, sketch the line to show the variation of the magnetic flux linkage in a coil C with position as it moves from X to Y. Of course, we know flux linkage. We know flux linkage is equal to number of turns B times A. The number of turns is constant, A is constant, flux density is constant, so the flux linkage is going to be constant. So I'll just draw a horizontal line. Where is my ruler? So I'm drawing a horizontal line, then Explain the shape of your line, of course. Magnetic flux linkage or magnetic flux density inside the solenoid is constant or is uniform. Magnetic flux density B inside a coil is constant, and flux linkage equals to NBA, and I will simply say all magnetic flux density B inside the coil is constant and flux linkage is equal to NBA, since all N, B, and A are constant, flux linkage is constant. Okay, so the flux linkage is constant. Then coil C is now held stationary at X. Coil C is now at X. The current in the solenoid varies so that the magnetic flux density B at X varies from T equals to 0 to T equals to 4T. Now, if the current changes, then it means the magnetic flux changes, so the induced EMF also changes because the magnetic flux linkage changes. Calculate the maximum flux linkage. So flux linkage is going to be equal to NBA, where B should be the maximum. So I'll just substitute this. Number of turns, I think it was 64. The maximum value of B is this one here, which is 0.080. The area was 0.7. The area was 0.71 centimeters squared. I have to change it to meters squared. So the area is 0.71. Is to change it to meters squared, I will multiply this by 10 to the power of -4. That is the area. So I'll press my calculator. 64 times 0.08 times 0.71 exponent -4. So this is 3.64 times 10 to the power of -4. 3.64 times 10 to the power of -4. Yes. On the figure, sketch a line to show the induced EMF. Remember, the induced EMF is directly proportional to the rate of change of flux. If flux doesn't change, the induced EMF is 0. If flux changes, there is an induced EMF. So between t equals to 0, t equals to t, between this point here, flux is constant. The induced EMF is 0. I'll increase the thickness slightly. So between t equals to 0 to t equals to capital T, the induced EMF is 0 because the flux is constant, because the magnetic flux density is constant. Then between t equals to small t to twice t, there's a change in the flux because the magnetic flux is changing, but at a constant rate because it's a straight line. T equals 2t to t equals to 4t, it is also changing, but it is also a constant rate. So it means there's an induced EMF here and an induced EMF here, but remember that this is a positive gradient, this is a negative gradient. So the EMFs, if the EMF here is positive, the EMF here will be negative. Let's check the gradient. Here we have two boxes. We have two boxes divided by on the x-axis. We also have two boxes. Then on the left-hand side, we have 1, 2, 3, 4 boxes on the vertical. 1, 2, 3, 4 boxes on the x. So the gradient is the same. So same gradient. same gradient. That means if the gradient is the same, it means same magnitude. Same magnitude of E, but opposite signs. Why are they opposite signs? Because one gradient is positive, one gradient is negative. So I will sketch that. So here because it is a straight line, it means the induced EMF is constant but not zero. So here will also be constant but not zero, but these are in opposite directions because the EMFs, the gradients were opposite. So that will be our graph. A metal spring rests on a smooth table. The turns of the spring are equally spaced. The ends of the spring are connected to a DC power supply as shown. Okay. The spring is connected to the DC power supply using flexible leads. The spring is not under tension, okay? It is relaxed. So let's say the current enters from here. So there's a current here. And if I consider these two corresponding coils, I have this one and this one. So there's a current here. Okay. So it's like they are carrying current in the same direction. Of course, there's a magnetic field around each of these turns. With reference to magnetic fields, describe and explain the change in the distance between the turns of the spring when the power supply is first switched on. First switched on because there is a change in magnetic field when it is just switched on before it becomes constant. So there's a change in magnetic field because they are carrying current in the same direction by Fleming's left-hand rule. If you remember the Helmholtz coils, if they carry current in the same direction, it's like they experience an attractive force. So it is like the coils, because if they are flexible, the coils are most likely going to move closer to each other. So I'll simply say the current in the spring creates a magnetic field around the spring. So if I consider just two turns, it means the magnetic field around each of the two turns or two neighboring turns are going to be interacting. So they will create a force on each of the turns, which force is going to be attractive. So the magnetic fields around adjacent turns interact to cause a force, to be exerted between the turns, to cause a force to be exerted between the turns. Of course, we have said by Fleming's left-hand rule on each of the turns, since they carry current in the same direction, the force is attractive. The magnetic force is attractive, so the distance between the turns decreases. Okay, the distance between the turns decreases. Okay, question number 7. I think this is now quantum physics. A photon has an energy of 3.11 times 10 to the power of minus 19 joules. capture the momentum of the photon. So we know that energy of, since they have given us photon, they have given us energy, they want momentum. We know that momentum of a photon, I'll use small letter p, is equal to energy divided by c. Energy is 3.11 times 10 to the power of minus 19 divided by c, which is 3 times 10 to the power of 8. 3.11 exponent minus 19 divided by 3 exponent 8. They want the answer in Newton seconds, so I'll just write 1.04 times 10 to the power of minus 27. A laser beam has a power of 350 milliwatts. The light from the laser has a wavelength of 640 nanometers. Determine the number of photons emitted by the laser in a time of 1.0 seconds. So we know that, let's begin by total energy. Total energy E is equal to power times time, which is 350 times 10 to the power of minus 3 times the time, which is 1.0 seconds. That is total energy. Then energy of one photon, energy of one photon equals to hf. They gave us a wavelength, which is going to be hc over wavelength. That is energy of one photon. So it means number of photons is going to be n times that. So if capital N is the number of photons, so I'll simply say E is equal to N times hc over wavelength. So which means N, I'll just equate this. So 350 times 10 to the power of minus 3 is equal to N times H, which is 6.63 times 10 to the power of minus 34. Then times C, which is 3 times 10 to the power of 8, divide by lambda, which is 640 times 10 to the power of minus 9. Okay, so I'm going to just press my calculator to find n. I'm making n the subject, which is 350 times 10 to the power of minus 3 times 640 times 10 to the power of minus 9, divided by 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8. So 350 exponent minus 3, 640 exponent minus 9. Divide by, first divide by 6.63 exponent minus 34, divide by 3 exponent 8. So that is 1.1 times 10 to the power of, I can write 1.13 times 10 to the power of 18. That is the number. The laser beam is incident normal on a surface that observes all the photons, so that the force F exerted on the surface by the laser beam is given by F is P over C, where this time P is not power, is not momentum, it is power. Yes, it is power. By definition, we know that force is defined as the rate of change of momentum. Force is the rate of change of momentum. So force is the rate of change of momentum. So I will say force is equal to the change in momentum. I'll write small p, not capital P, because this time capital P has been used for power. So force is equal to small p over t. But we also know that the momentum small p is equal to energy divided by c. So it means the force, whether it's changing momentum, I'll put E over c. So the force is going to be equal to E divided by T times C. And of course, we know that power, capital P, is equal to energy over T. So it means the force, where there is energy over T, the force is E over T times 1 over C, which means force is equal to power over C as required. Okay. Light of a single wavelength is incident on the surface of different metals. The work function energy of the metals is given in the table. Explain the term threshold wavelength. Remember, threshold frequency was the minimum frequency. So the threshold wavelength is the opposite, is maximum wavelength. If threshold frequency is the minimum frequency of electromagnetic radiation, below which no photoelectric emission occurs, it means threshold frequency must be the maximum above which no photoelectric emission occurs, simply because frequency is inversely proportional to wavelength. If F naught is maximum, then F lambda, if F naught is minimum, then F lambda naught must be maximum. So this is going to be the maximum wavelength. The maximum wavelength of electromagnetic radiation that causes electrons to be emitted from the metal surface. The maximum wavelength of electromagnetic radiation that causes electrons to be emitted from the metal surface. That's what we call a threshold wavelength. Okay, for the metals in table 7.1, calculate the value of the largest wavelength. If wavelength is largest, it means calculate the value of the largest wavelength. For the wavelength to be largest, it means the frequency must be lowest. That means we must take the smallest work function. Because we know that the work function energy, which I normally prefer to write as phi, is equal to h times F naught, which is h c over lambda naught. So we want the largest wavelength. The largest wavelength should correspond to the smallest work function. So it means lambda naught is going to be hc over phi, which is going to be the smallest. So this is going to be h. Did I make? Okay, I hope I made this the subject correctly. What is given is work function. Okay, so this is going to be a 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the energies, the smallest work function is this one here, which must be changed from electron volts to joules. So from electron volts to joules, I multiply by 1.6 times 10 to the power of minus 19 to change it to joules. So this will be divided by 2.26 times 1.6 times 10 to the power of minus 19 to change it to joules. So I'll check my calculator. 6.63 exponent minus 34 times 3 exponent 8 divided by 2.26 times 1.6 exponent minus 19. So this is giving me 5.5 times 10 to the power of minus 7 meters. 5.5 times 10 to the power of minus 7 meters. Question 8 is nuclear physics. State what is meant by binding energy of a nucleus. Of course, if you have watched my videos for nuclear physics, you now know that binding energy is the minimum energy required to separate minimum energy required to separate the nucleons of a nucleus to infinity. Minimum energy required to separate the nucleons of a nucleus to infinity, that is binding energy. The nucleus of uranium-235 absorbs a neutron and becomes unstable. It then undergoes fission reaction. One possible reaction is shown here. Determine the number of neutrons produced in this nuclear fission. So neutron, remember neutron is 1, 0. So let's put X here on the X-axis. The proton number is conserved. It's only the nuclear number which is not conserved. So we shall just say 235 plus 1 on the left-hand side minus 142 plus 90 on the right-hand side, so that the difference is going to give us the number of the number of neutrons. So we have 236 minus 142 plus 90. That is 4. So there are 4 neutrons. When I say 4 times 1, it is 4. So the nuclear number is balanced. Data for the binding energies per nucleon. This is per nucleon for the fission reaction are given in the table. Calculate the energy released in mega electron volts from the fission of one nucleus of uranium. Okay, so on the left-hand side we have uranium, whose binding energy per nucleon is given here. On the right-hand side we have these two. Of course, we shall assume that the neutron, the term binding energy does not apply to the neutron, so I will not consider the neutron here because it is not included in the table. So the difference in the energy is going to be equal to the energy released, but we want the energy in mega electron volts, not binding energy per nucleon. So the energy released is going to be equal to the difference in the energy on both sides of the equation, which is going to be equal to, on the right hand side we have xenon, which is going to be 8.37, that is energy per nucleon. So I have to multiply by the nuclear number. So this is times 142. Plus, we have also strontium, which is 8.72. That is energy per nucleon, then times the nuclear number, which is 90. So this is on the right-hand side, minus on the left-hand side, which is going to be 7.59 times the nuclear number, which is 235. So let's check this. 8.37 times 142 plus 8.72 times 90 minus 7.59 times 235. So this is giving me 189.7, 189.7. Or I can write 190 approximately, because this is 69. So approximately I can write 190 mega electron volts. So the difference in energy is the energy which is being released. The isotope xenon is unstable. the isotope xenon 13 is stable. Suggest a reason why xenon 142 is unstable. Let's check the neutron to proton ratio of these ones. So if I check Xe 142, I think the proton number was 54. This one has a number of neutrons 142 minus 54. So that is 82. So the ratio of N over P is going to be 88 divided by 54. Divided by 54. This is a 1.6, very close to 2. Let's check Xe 132, 54. 132 minus 54, that is 78. So the ratio is 78 over 54. So this is 1.4. So this is less than, this is a smaller ratio. So we are going to explain in terms of the neutron to proton ratio. So I'll say Xe or xenon 142 has too many excess neutrons for the number of neutrons. So its neutron to proton ratio is too high. So its neutron to proton ratio is too high. You'll always find that most stable nuclei have a proton to proton ratio which is very close to 1. For those nuclei whose proton to neutron ratio is very close to 2, they are always unstable. Like xenon 1.6 is very close to 2. The other one, 1.4, is very close to 1. So xenon 142 has too many excess neutrons for the number of protons, not number of neutrons. For its number of protons, so its neutron to proton ratio is too high. As we have seen, the other one is close to 2, this is close to 1. So the neutron to proton ratio for 142 is too high. Then xenon 142 decays into the isotope cesium 142. A sample initially contains only nuclei of xenon 142. After a time of 6 seconds, the ratio number of undecayed nuclei. If we say that original number is n naught, the number which decays is n. The number present after a certain time is n. So it means the number of undecayed is going to be n naught minus n over the that is the number of decayed, n naught minus n. This is initial, this is present. Initial, present after a certain time. What has decayed is the difference. What has not decayed is what is present, that is n. So they are saying n naught over n naught minus n over n is 31. So this is equal to 31. Calculate the half-life of xenon 142. Show your working. So we have already seen that n naught minus n over n is equal to 31. Number which is decayed is the difference. Number which is undecayed is what is present, that is n. So if you do the mathematics here, I think you will notice that this means n naught minus n is equal to 31n, or you can say n naught is equal to 32n, or you could say n over n naught is equal to 1 over 31. 1 over 32. When I divide both sides on the left hand side by 32, I have n over n naught is equal to 1 over 32. Okay? But I also know that n is equal to n naught e power minus lambda times t. And I know that lambda is equal to ln of 2 divided by t a half, or half-life. So n over n naught is going to be e power minus, where there is the decay constant, I'll put ln of 2 over t a half, that is decay constant, then times t. So I'm now just going to substitute. N over n naught is 1 over 32 equals to e power minus ln of 2 divided by half-life, which is what I want to find, t a half, times t, which was 6. So introducing ln, I have that ln of 1 over 32 is equal to ln of the right hand side. I have only the power, so it is going to be negative 6 ln of 2 divided by t a half. So making t a half the subject, t a half is going to be negative 6 ln of 2 divided by ln of 1 over 32. So I'll just press my calculator. I'll start from the denominator, ln of 1 divided by 32. Then I get negative 6. I'll have to put this in brackets. Negative 6 ln of 2 divided by the answer. So I have 6 over 5, which is 1.2. So the half-life is going to be exactly 1.2. Okay. I think this is still quantum physics. Electrons in a vacuum are accelerated through a potential difference of 84 kilovolts. It could be medical physics. The electrons then strike a metal target and X-rays are produced. Calculate the minimum wavelength of the X-rays that are produced. Of course, the kinetic energy of the electrons is what becomes the X-rays. So I will say kinetic energy of the electrons is going to become the photon energy. So the energy of the electrons is given by E, or charge times accelerating PD. And the photon energy is equal to HF, which is Hc over wavelength. So the wavelength is going to be Hc divided by E times V. So H is 6.63 times 10 to the power of minus 34. C is 3 times 10 to the power of 8 divided by E. 1.6 times 10 to the power of minus 19 for the electron. The accelerating speed is 84,000. So this is going to be times 84,000. I'll just press my calculator. 6.63 exponent minus 34. 3 exponent 8 divided by 1.6 exponent minus 19. I have again to divide by 84,000. So I'm getting 1.5 or 1.48. 1.48 times 10 to the power of minus 11. The melting point of the two metals are given in the table. We have tungsten, we have copper. Suggest why the metal target is made from tungsten rather than copper. You notice that the melting point of tungsten is very high. It's almost 3 times that of copper. Why is it so high? Remember, your teacher must have told that almost 99% of the energy, the kinetic energy of the electrons becomes heat in the metal target. So we need a metal which has a high melting point so that it does not melt very easily. So we'll say most of the kinetic energy, most of the kinetic energy of electrons is converted to thermal energy. Thermal energy at the target Most of the kinetic energy of the electrons is converted to thermal energy at the target. So the temperature increases. But tungsten has a high melting point. Tungsten has a higher melting point, so does not melt easily. So because tungsten has a higher melting point, it will not melt easily. What we mean by high melting point means it requires too much heat for it to melt. So it does not melt easily. An X-ray beam is incident normally on a sample of soft tissue and bone as shown in the figure. Data for the two materials are given in the table. So they have given us data here in the table. They have given us the medium, they have given us the linear attenuation coefficient, and they have given us the specific acoustic impedances. The total thickness of soft tissue is X. The total thickness of bone is X. So that means bone is X. When I add this thickness here to this thickness here, total is X. So since it is the X-rays must pass through the soft tissue twice, instead of multiplying this and this, I'll just consider the total thickness here because I would add this intensity here to this one here. Then I will multiply with this one here, the intensity which goes through this one here. Okay, so determine X in centimeters. So we know that intensity transmitted through any medium is equal to I naught e power minus mu times t, where t is going to be the thickness. Since X has already been taken, I'll use t for the general equation. Okay, they say the incident intensity of the X-ray beam is I naught. The transmitted intensity of the X-ray beam is 13% of the incident. So it means I is 13%, that is 13 over 100 of I naught. So it means I is equal to 0.13 of I naught. So I divided by I naught must be 0.13. So, and of course you notice that I over I naught is going to be e power minus mu as attenuation coefficient. So it is going to be if I consider soft tissue first, it will be 0.22 times its thickness, which is X. That is this is for soft tissue. Then I'll multiply this by e power minus, because it also goes through bone, its thickness is X. Its attenuation coefficient is 3, so it is minus 3.0 times X. So I'll simply say 0.13 is equal to, this is E power, of course I'll just add up the powers. So this will be E power minus 0.22 and 3, that is I think 3.22. Because of multiplication, I'm adding the powers, so minus 3.22x. I will introduce ln so that I find x. So I'll say ln of 0.13 is equal to the power, which is minus 3.22x. So x is going to be equal to ln of 0.13 divided by negative 3.22. So ln of 0.13 divide by negative 3.22. So I'm getting 0.63. or 0.634 centimeters. Define the specific acoustic impedance of a medium. We know that Z is equal to rho times C, the density of the medium times the speed of the ultrasound in that medium. So I'll simply say product of the density of the medium and the speed of ultrasound in the medium. The product of the density of the medium and the speed of ultrasound in the medium, that is specific acoustic impedance Z. Use data from the table to calculate the percentage of the intensity of ultrasound that is transmitted at the boundary. Every time we see at the boundary, we want transmitted, not reflected. So fraction reflected, that is the intensity reflection coefficient, which you normally represent as alpha, or intensity R, IR of I naught is the same as Z2 minus Z1 over Z2 plus Z1, and this is always squared. So this is the same as, let me check the powers of 10. The powers of 10 are the same, so I will not consider the power of 10 because it is the same. So it is going to be 7.8 minus 1.7 over 7.8 plus 1.7, and this is squared. Remember, this is the fraction which is reflected at the boundary, not transmitted. So 7.8 minus 1.7 divided by 7.8 plus 1.7, but this should be squared. So this is giving me 0.41. I'll write two significant figures. 0.41. That is the fraction reflected. Then I'll write the fraction transmitted. Of course, the fraction transmitted will be 1.00 minus 0.41 because the total should be equal to 1. So, of course, this is going to be 0.59. Then it means the percentage is simply going to be 0.59 times 100, which gives us 59. Okay, then the ultrasound is now incident on the sample of soft tissue and bone shown in the figure. Suggests two reasons why the transmitted intensity through the sample is less than the answer in C Roman 2. First of all, we have not considered the transmitted intensity is less than they said suggest two reasons why the transmitted intensity through the sample is less than the answer in C Roman 2. So why should the transmitted intensity be less than this? It is most likely going to be less than this because one, we expect that it is going to undergo absorption. First of all, it undergoes absorption or it is attenuated in the matter before reaching the boundary. Secondly, there could be more boundaries. Even from the diagram, we see more boundaries. So there could be more boundaries within the matter or within the tissue, which boundaries would cause more reflections. So those two factors may affect the transmitted intensity. So let's say some ultrasound is absorbed, or we can use the term attenuated. Attenuated in the matter before reaching the boundary. That's number one. Number two, there are more than one boundary. We expect that there could be more than one boundary in the tissue. There are more than one boundary. So more reflections occur. Because for every boundary we expect reflection. So there are more than one boundary, so more reflections occur. This would reduce the intensity which is transmitted. Okay, the last question, I think this is going to be astrophysics and cosmology. The sun has a surface temperature of 5780 Kelvin. The luminosity of the sun, this is capital L, is 3.85 times 10 to the power of 26 watts. Calculate the radius of the sun. Of course, they gave us this Stefan Boltzmann's equation. L is equal to 4 pi r squared, 4 pi r squared times sigma times t to the power of 4. So the luminosity is given as 3.85 times 10 to the power of 26, equaling to 4 pi times r squared times Stefan Boltzmann's constant is 5.67 times 10 to the power of minus 8. It is always given in the list of constants. The temperature is 5780 power 4. So I'm just going to press my calculator. So 3.85 exponent 28 divide by, I'll first divide by 4 pi. I'll divide by 5.67 exponent minus 8. Then I'll divide by 5780 power 4. So that is, I'm getting, of course, I have to find the square root because r is squared. So I'll find the square root of the answer. So this is 6.96 times 10 to the power of, I have to count this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it? 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is times 10 to the power of 9. I think I used the wrong power here. I have to check this again. This is power 26, not 28. So if it is power 26, 3.85 exponent 26 divide by 4 pi times 5.67 exponent minus 8 divide by 5780 power 4. Then root of the answer. Okay, so it is power 8, not power 9. Then the Earth is a distance of 1.5 times 10 to the power of 11 meters from the Sun. Calculate the radiant flux intensity F. Of course, we know that F equals to L over 4 pi d squared. So luminosity is 3.85 times 10 to the power of 26 divided by 4 pi, then times d. D is 1.5 times 10 to the power of 11, but this should be squared. Of course, this is a radiant flux intensity, which should be watts per meter squared. You can even see L is in watts, D is squared, so it is per meter squared. So 3.85 exponent 26 divided by 4 pi. Let me first divide that. Divide by 1.5 exponent 11, but this should be squared. So I'm getting 1360 1360 or 1361, I mean 62, or you can write 1360 watts per meter squared. The variation with the wavelength of the intensity of the radiation emitted from the sun is shown in the figure. Okay. Remember, we know that the wavelength at which maximum intensity occurs is always inversely proportional to absolute temperature. Another star has the same radius as the sun, but has a lower surface temperature. So when the temperature is small, it means the wavelength at maximum intensity is going to be small. Of course, if the wavelength is small, it also means the intensity is going to be smaller. On the figure, sketch the line to show the variation with the wavelength. So first of all, the wavelength, if this peak is here, the other peak should be on the right-hand side because it's of a lower wavelength, and wavelength is inversely proportional to temperature, and the peak is going to be smaller and even more flatter. So I'll draw something like this. Okay, that is going to be the peak. So that is going to be the graph. First of all, the wavelength is greater. You see the peak here is at a higher wavelength than the one before, which was here. Secondly, of course, because at lower temperature, the wavelength is greater, so it must be to the right-hand side. Then, of course, a higher temperature, I mean, a, 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 a greater wavelength. I mean, this is higher, so it points upwards. A higher wavelength corresponds to a smaller intensity, so this is going to be the intensity is going to be lower. A galaxy in the constellation Corona Borealis is moving away from the Earth. It is away. The visible emission spectrum for the Sun is shown in the figure. The lines are at wavelengths 397, 410, 434, 486, and 656 nanometers. The compositions of the Sun and the star in the Corona Borealis galaxy are similar. On the figure 10.3, because the compositions are similar, sketch the emission spectrum for the star in the Corona Borealis galaxy as observed from the Earth. No calculations are required. Okay. So we are looking for 397. So 397 is going to be closer to 400. So I'll draw it here. I'll increase the thickness. So I'll draw it somewhere here. Then 410 is just after 400. So because this is 400 and 450, 410 could be around here. Then next is 434. Of course, 434 is just after the center. So I would put it around here because at the center is 425. So I will put it around here. Of course, I must be very careful with the difference between these. Then the next is 486. So 486 is closer, is after 475, which is at the center. So this is going to be around here. Then the next is 656. 656 is going to be between here. Of course, the center is 675, so 656 could be very close here. Okay, so of course the lines increase in separation. The separation of the lines is increasing. Okay, the galaxy, because they are already shifted anyway, the galaxy is in Corona Borealis is moving away from the Earth at a speed of, so this is V, 311,400. Use the information in B Roman 1 to calculate in nanometers the observed wavelength for the lowest visible energy emission. Note that energy is inversely proportional to wavelength. So the lowest visible energy emission implies the greatest wavelength. So the greatest wavelength, we are using information in B Roman 1. and the information is going to give us 565 as the greatest wavelength. That is the greatest wavelength, 565. So using the Doppler redshift equation, lambda change in wavelength is equal to V over C. So we can first find the change in wavelength, which is going to be V, which is 21400 times 10 to the power of 3, divided by C, which is 3 times 10 to the power of 8, times the wavelength, which is 656. So what is the change in wavelength here? 21400 exponent 3 divided by 3 exponent 8 times 656. So the change in wavelength is 46.8. So it means the wavelength we are talking about is going to be 46.8 plus 656. That is the wavelength we are talking about here. That is the new wavelength. So that is going to be plus 656. So this is going to be 703 nanometers. Okay, that is the wavelength of the lowest visible energy. The wavelength in B Roman 2 is used to calculate a value for the surface temperature of the star in Corona Borealis galaxy. Remember, the wavelength at maximum intensity is inversely proportional to the absolute temperature. And we are seeing the wavelength is bigger. So if the wavelength is bigger, the temperature is going to be smaller. State and explain whether this value of temperature is too high or too low. So it is going to be too low. So we are seeing that the wavelength at maximum intensity is too high, or the peak wavelength is too high in comparison to what we saw in part 2. The peak wavelength, part 1, the peak wavelength is too high. So from lambda max inversely proportional to temperature, the temperature is too low. And I think that marks the end of paper 4. See you in another paper. Until next time, bye bye.